Hello, my name is Mr. Macquarie. A warm welcome to this presentation on forces. This is the second lesson in the sequence on forces and is entitled Resultant Forces. So before we start, let's find somewhere that is quiet and free from distractions to allow us to work. And we will need a pen, paper, ruler and a pencil to help us with diagrams today. So if you need to pause the presentation to collect those, please do that. So let's have a look at our starter then. First of all, the title of Resultant Forces underlined nicely in the middle. I'd like you then to sketch a diagram of a free-fall character, and underneath it I'd like you to list the number of forces that are acting in this figure. And to do that, I'd like you to use your knowledge from the first lesson in this sequence to draw a free body diagram and label the forces involved in that. Okay, let's have a look at what that diagram should look like, and let's just make sure that we have drawn it in the correct way. So the number of forces acting in the diagram is 2, and I have listed them there as air resistance and weight due to gravity. So first of all, you need to make sure that you have done the following. Number 1, that the arrows are drawn to scale for the correct size of the forces, and number 2, that the arrows are drawn from the center of mass of the object. And I'd like you to do that for all of the free body diagrams that you have in today's presentations. So let's have a look at our challenge. First of all, to be able to calculate the resultant force on an object. That should not be too taxing and won't require a calculator for the knowledge numbers we have today. They aspire to be able to predict what an object will do according to the forces applied. So we need to have a good understanding of the laws of motion in physics. So in lesson number 1, we have looked at the following, and let's just recap using the same diagram from the previous slide. First of all, we should know that a vector quantity may be represented by an arrow, that the length of the arrow represents the magnitude or size of the object, that the direction of the arrow represents the direction of the force, and finally that forces always act in equal and opposite pairs. There can be more than 2 forces acting on an object, but in this example we just have the 2 forces there. So let's apply our learning now. Here we have a photograph of a person who is stood still on a surface. I'd like you to draw a sketch diagram of that person, maybe 4 or 5 lines long. Perhaps put a line under their feet to show the floor. I'd like to know how this person is being pulled. I'd also like to know how you can tell that the person is experiencing a pair of forces. So what forces are occurring on that person. And then finally, an interesting one, what needs to change for this person to rise or sink? So I'd like you to draw a free body diagram that shows this person just stood on the surface. You've got a minute and a half. Okay, let's look at the answer, make sure that we have followed the correct formatting for that. First of all, I've got a figure and I've put a dot in the center of mass of the person. We have an arrow representing the weight due to gravity pulling the person into the ground, but then we have an equal arrow which shows the force of the floor pushing upwards at the person. Because the forces, person is stood still, the forces are balanced. If the floor was quicksand and not concrete, then the upwards arrow would be smaller, which would mean that the person would sink, and the forces would be unbalanced to cause that. So if we understand those points, we will move swiftly onwards. If you could make sure that you have explained and corrected your diagram at this point, that would help our learning later. Just make sure that we're continuing to use the correct arrows and dots, etc., sizes of arrows for our free body diagrams throughout today's lesson. Okay, so we're going to have some practice now in drawing a free body diagrams. We're going to draw diagrams of the following, point 1, 2 and 3. We're going to use force arrows of different sizes and directions when necessary. Now what I would like you to do is to put each of the small questions that are down there, just in case your diagrams like mine are shortly going to be unrecognizable really, as I'm not good at sketching. So the first diagram I would like you to draw is of a climber who is suspended stationary by a rope, and I'd like you to make that into a free body diagram showing the forces that are applied. Okay, so in answering question 1, let's just be clear that you've labelled your 2 forces on the stationary character who is suspended by the rope, and that you have shown the size of the forces by the length of the arrows. Okay, let's move on to question 2, and I'll run through the answers with you afterwards. So for question 2, a person pushes a shopping trolley along at a constant speed. Okay, so I'd like you again to draw a small sketch diagram showing the forces, and make sure that you put the centre of mass of the trolley and the forces labelled. Okay, and let's move on to our third free body diagram. Again, write the introduction down. A rocket is accelerating in deep space. So obviously I've chosen those words carefully. Let's see if you have an understanding of the forces that are involved. So we have then a rocket accelerating in deep space. Okay, and we'll now cut to a clip and I'll show you the answers. Okay, let's have a quick look at the free body diagrams that we have got. These are sketchy, but they will do. First of all, we have a climber. It says a stationary suspended by a rope. If they're stationary, that must mean there are balanced forces acting on that person. So we have the pull of the rope as an arrow, which should be from the center of the body of the climber, and then we have equal sized arrow showing the weight of the climber. Okay, let's look at the second one, which we have a shopping trolley. Okay, so if that person is pushing the trolley at a constant speed, then the push force from the person arrow must be the same size as the air resistance and friction arrow acting in the opposite direction. Okay, it's a very simple diagrams, again acting on the center of mass of the trolley. And the final one is one for interest. We have a question here about a rocket in space. The rocket is accelerating. So obviously we have no air in space, so we have the push force or thrust of the rocket from throwing burning fuel out the back. Newton's third law says that it will be equal and opposite, so therefore the force forward will occur, but we don't have any air particles, so therefore we just have a single arrow facing it in a forward direction. So let's just look for a moment at some of the laws of physics. These are then going to be extended to allow us to look at the challenge, so we can see where resultant forces come from and how they fit into what was said by Isaac Newton here. Things will go in the same direction at the same speed unless another force changes this. So we need to understand the implications of that, and we've been doing that and showing that with our free body diagrams. Let's continue. Things will go in the same direction at the same speed unless another force changes this, or if the sum of forces acting on it totals 0, it's making the same point, the sum of the forces is called the resultant force. Now what I would like you to do at this point is to spend a couple of minutes now just writing those 3 statements that we have there, because they are important statements, and it leads us to build up some science with the word resultant force. So I'm going to give you 2 minutes to allow you just to get those notes down. Do them as bullet points, please. I think that would be simpler at this point. 2 minutes, please. Okay, if you need to pause the presentation to complete those notes, make sure you've underlined the word resultant force as well. And we're now going to look at those particular calculations. Okay, so let's now do some application of our new word resultant force and make sure we can do some calculations. If you supposed for a moment that we had two donkeys fighting over a shopping trolley in a supermarket, and one of them was pulling the trolley with a force of 100 newtons and the other was pulling in the opposite direction with a force of 100 newtons, the calculation of resultant force would look like this. So here's one donkey and here's another pulling with a force of 100. So let's look at the answer for a second in maths this time, rather than a picture diagram, free body diagram. Forces are opposite directions, but they are equal. So if we add them together, we've got 100 newtons acting in one direction, and we are going to subtract 100 newtons in the other direction, which gives us an overall answer of 0 newtons. The trolley does not move as the resultant is 0. Now I hope that's clear. If we need to put that in your notes, then pause the presentation to do that now, but I would rather move to the next example. If a donkey pulls with a force of 100 newtons and another pulls in the opposite direction with a force of 50 newtons, what is the resultant force in this example? So let's look at that. Here's our donkeys. So what do you think would happen in this example? Which way would the trolley move? What would be the resultant force? So let's look at that. The forces are in opposite directions, but this time are not equal. So if we add them together, we've got 100 newtons in one direction, and we're going to subtract them from each other, giving us a leftover force of 50 newtons to the left. So the trolley moves towards the left with a force of 50 newtons. Okay, we're now going to look at some more examples, but I want to just be secure in our use of free body diagrams, especially as we're dealing with vectors which need a direction. So I want to be clear that in this particular page I'm going to be using a compass symbol. We have north acting up the page, which means we've got east to the right of the page, and we have west to the left of the page. Just be clear that we know those points. So our free body diagram here, we have a car with a thrust force pushing forwards of 5,000 newtons and some resistance, wind resistance of 2,000 newtons. So what would be the resultant force in that diagram, and which compass direction would it be acting in? So I hope you can see that the answer would be 3,000 newtons, and the direction of travel using that compass point would be west. Now we could have said left if that had been the question and the way that it was asked, but I want you just to learn to take whatever the question gives you and adapt your answers to ensure that you give a direction in the format that the question is asking for. Now let's look again, this time using a boat. It's got divided forces in this case. So we have 2,000 newtons from the engine acting east. We have 1,000 newtons from the wind, again acting east. And we have 500 newtons from friction, which are acting west. So work out your resultant forces from that diagram. Let's have a look at our answers for a moment. So we have then a resultant force of 2,500 newtons in total acting east. Where did that answer come from? Well, if we add together the 2,000 and 1,000 newtons which are acting east. We end up with 3,000 newtons in one direction. Those are unbalanced forces. We have 500 newtons here acting west, and we're going to subtract that from it, leaving us with a resultant force of 2,500 newtons acting east. So as long as we take the format and we take the information in the question, we should be able to do some simple calculations using resultant forces. So force is a vector quantity, so we need to always state the direction of a resultant force. For example, up or down or left or east, whatever is required in the question. That's important that we remember that. So let's do some application. Okay, now I want to work through this example with you now, and I also want to use it to expose a problem, and it allows me to point that problem out to you in the amount of information that is needed to be able to effectively answer a question. So what I would like you to notice first of all is that we have a north arrow again at the top of the page here. I've put the centre of mass on the car. We have a thrust force of 3,500 newtons and a resistance force of 2,000 newtons, air resistance. So what I would like you to do is I'd like you to calculate the resultant force, which I think you should find quite straightforward, but to tell me in which direction it would be acting. Are the forces balanced or unbalanced, which again should be a simple question for you at this point. And I am very deliberately leaving you with that amount of information at the moment. So over to you. Okay, so let's just look at the answers. First of all, it's very straightforward, I hope. So calculate the resultant forces. If north is up the page, then we need to be going in this direction, which is west. The resultant force is 1,500 newtons, subtracting these two from each other. So 1,500 newtons west. Are the forces balanced or unbalanced? The forces in this case are not the same, so they must be unbalanced. And what is happening to the car? Well, the car is travelling west and would be accelerating. Now, my question for you is, if I made this force here 3,500 newtons, 2,000 newtons, and we then looked at the questions again, how would they change? So if they were both 2,000 newtons, the resultant force would be 0. Are the forces balanced or unbalanced? Well, the forces are balanced because they are the same. But it's question 3 here that we need to be careful with, because we need to know something about the car and the balanced forces. First of all, we have to acknowledge that the car could be stood still, that the force of friction trying to get the car moving and the force of the engine may be balanced and the car may not be moving. Or it may be the case that the car is moving at a constant speed with balanced forces. And we're going to explore this issue as we move on to the next few slides, because we need to know what is happening to the car before we start answering the question at some points. So information is needed, and this is the point again that I would like to make. It's not always obvious from free body diagrams of what is happening. We've got two figures here. Both of these figures are identical. They have equal sized arrows. One is standing still on the ground and the other one is falling from the sky at a constant speed. As we've seen, this is a diagram we drew at the start of the lesson. If this is the person stood on the ground, if they're stood still, the forces are balanced. They're neither moving upwards or downwards. But a person falling out of an aircraft who's accelerated to a constant speed, the force downwards, the weight due to gravity, is matched by the wind resistance, and the person falls at a constant speed. So in describing a diagram, it's important that we understand what exactly is happening in terms of movement and what the context is, so that we can apply the labels and forces correctly. So we're now going to apply what we just said to this diagram here. We have to pick up some cues from this particular diagram and photograph to help us. It's very clear, for example, that the car is moving. So here are the questions I'd like you to answer on your paper, please. What is the resultant force? Are the forces balanced or unbalanced? The vehicle is not stationary, so if the resultant force equals 0, explain please in writing what is happening. I'm going to give you a minute to do that. Okay, if you need to pause the presentation to carry on writing for a moment, do that. But let's just explore this particular issue. Let's make sure that we get over this before we finish the presentation today. The resultant force is 0. 2,000 newtons thrust force and resistance force of 2,000 newtons. The forces must be balanced because they are the same side. But we've been told in this question that the vehicle is not stationary. So if the vehicle is not stationary, we need to be clear in our explanations about how the forces can be balanced and yet the vehicle is moving. So we have a resultant force of 0. So the vehicle is being pushed forward by the force provided by the engine of the vehicle, but as it moves forward, the air resistance of hitting particles will eventually balance the push force of the engine, resulting in a balanced force, a resultant force of 0, and yet the vehicle is moving. It's moving at a constant speed in this example. Same thing would happen with the skydiver, and I'm going to give you that as an example that you will need to work on as we move forward. So we have now increased our understanding. We should be able, for example, to calculate the resultant force on an object. And for our aspire to predict what an object will do when a number of forces are applied, we have learnt to be very careful about finding out the circumstances of an object and to pick up the cues from an object to describe its motion. So we're going to develop some notes now. So I'd like you in your book, please, to draw the following table. And we are going to put some sentences under the correct columns of balanced forces and unbalanced forces. So you're going to be given some statements and you will need to decide whether they describe a balanced force or an unbalanced force. So with a pencil and ruler, if you could please just draw that table. Got a minute and a half. Okay, so you've got your table with balanced forces and unbalanced forces on your page. So if you haven't, you need to do that now before we move forward. So using your table, I'm now going to give you 3 minutes to write the following statements into the correct column on your table. So I'm going to put all of the statements down for you. And what I would like you to do is to then put those statements, deciding whether they are balanced descriptors or unbalanced descriptors. So I'm going to give you 3 minutes, 2 1.5, to allow you to do that, to make your decisions and to write them in. Okay, so you should have made a decision about each of those statements. So we have got then balanced and unbalanced forces. First of all, let's start with the balanced forces. If the resultant force is 0, then subtracting the two forces must mean they are balanced. If something was not moving, then it will stay still. So again, the forces on that object must be balanced if it's staying still. E, if something was already moving, it will continue moving without getting faster or slower. So again, that's an application of a balanced force. That could be, for example, a car traveling at a constant speed, or that skydiver traveling at what's called terminal velocity or a constant speed. Then we've got our unbalanced forces. Let's see why they're unbalanced. First of all, a resultant force exists. So we've got two forces acting, but one of them is larger than the other. So we have a number that tells us that the force is unbalanced. There will be a change of direction that must be unbalanced to cause that to occur. And we saw those in the laws from Isaac Newton earlier. Something will get faster or slower, accelerate or decelerate. That must again be unbalanced because there is a resultant force being described in that sentence. Now, there's an opportunity now just to pause the presentation and make sure that you have got those statements in the correct columns. It's important that you do that. Have a really hard think about why each of those sentences must be in the column that it's currently drawn in. Okay, these diagrams are drawn in a way that we would use them in Key Stage 3 currently, and they are in need of improvement work. So what I would like you to do for each of these as we now move towards the end of this particular presentation today is to convert each of those diagrams into a proper free body diagram using a center of mass and correct size arrows showing the size of the force. What I'd like you to do then is to describe what each of the objects will do. Now you can use compass directions, or you can use forwards, backwards, etc. But I would like you to calculate the resultant force for each of them. So you have got a minute and a half for each of the diagrams, and the descriptions are there, so you'll need to work quickly to allow that to occur. Off you go. Okay, let's move on to our second diagram now. So we've got this person with a space pack on. I'd like you to look at the forces and to draw a correct free body diagram with a center of mass and correct size arrows. and I'd like you to describe what the object will do calculating the resultant force. Okay, let's look at the approximate answers. Please excuse the quality of these diagrams. My goodness. So what I've done then is I have shown the direction of travel. I have subtracted successfully 1,700 newtons, 1,000 from that, and ended up with 700 newtons going to the right. Let's look at the second one. Again, center of mass indicated, and we have a 1,000 newtons going to the right, showing the direction of travel. So hopefully you've got answers that look something like that on your page in front of you. So welcome to our plenary. This is a Harrier jump jet, something you'll find in a museum these days, although there is a newer version of it being produced now. This plane was clever because it could take off and land vertically. It was also capable of hovering. So I've got some simple questions for you down at the bottom of the page. If gravity pulls on the plane with a force of 27,000 newtons, I need you to demonstrate and be able to justify your answers to the following questions. Question number one, I'd like you to write down, please, the minimum thrust required from the engines for it to just take off vertically. And second question, the thrust required to make it hover. So I'm going to give you a minute and a half to think about those and write your answers down. Okay, so the gravitational pull on the aircraft is 27,000 newtons. So therefore, the minimum thrust required from the engines to make it take off must be literally just higher than 27,000 newtons. So therefore, 27,001 newton would cause that aircraft to take off. If I wanted it to take off quicker, then I would unbalance the forces by a larger amount, and that would cause that to occur. So hopefully you've written a number greater than 27,000 newtons as your answer. It did require the minimum thrust though, so 27,001 newtons would be the correct answer. Number 2, the thrust required to make it hover. Now, if an object is hovering, there must be an indication of balanced forces. So therefore, to make an object hover with a gravitational pull of 27,000 newtons, the thrust from the engines of the aircraft must also be 27,000 newtons. So welcome to our final slide today, and we'll have a look at our learning outcomes. For our challenge, we have done lots of calculations of resultant forces on an object, and for our Aspire, you should now be able to predict what an object will do according to the forces applied. Thank you and goodbye.